most productive and regenerative permaculture and agroforestry system to solve the world's environmental, pollution, inequity, economic and most other problems. This is a complete, deeply detailed guide on how to create the most productive, climate-resilient, multi-season permaculture system that yields food year-round, resists drought, restores ecosystems, and builds long-term fertility. How to create the most productive and resilient permaculture for every season of harvest. Designing a year-round permaculture system means building self-maintaining ecological cycles that constantly feed each other, water cycles, nutrient cycles, plant-animal cycles, sunlight capture, and microclimate engineering. The goal is to make the system so regenerative that it keeps producing regardless of weather, season, or climate stress. Here is a blueprint you can apply anywhere: temperate, tropical, drylands, cold climates, or mixed conditions. Begin with the foundation: soil, water, climate, and layout. Build healthy, living soil. Healthy soil equals year-round food. Use deep mulch, wood chips, straw, leaves. Add biochar charged with compost tea to store nutrients and water. Maintain permanent root systems, perennial crops. Keep soil covered with living groundcovers, clover, vetch, creeping thyme. Plant mycorrhizal inoculated trees. Avoid tilling, protects microbes and water-holding structure. Outcome: soil acts like a sponge, cool, moist, fertile year-round. Manage water to eliminate drought stress. Water is life. Your design must slow, spread, and sink it. Layered water strategy: swales on contour for rain infiltration. Ponds and mini reservoirs for seasonal storage. Terracing steep slopes. Gray water irrigation from showers, sinks. Drip irrigation and oyas during dry months. Mulch plus trees plus shade reduce evaporation. Even in dry seasons the land stays hydrated. Shape microclimates. Microclimates allow year-round productivity. Windbreak trees create warmer winter pockets. Sun traps and U-shaped tree arrangements capture heat. Shade trees cool summer crops. Thermal mass, stones, walls, stores heat for night. You can grow tropical crops in temperate zones and winter greens outdoors. Diversify with a multi-layered food forest. The heart of productivity. The 7 layers ensure resilience and constant harvest. Canopy, nut trees, tall fruit trees: chestnut, pecan, walnut, mulberry. Subcanopy, citrus, peaches, pears, apples. Shrub layer: blueberry, raspberry, currants, sea buckthorn. Herbaceous layer: basil, sage, mint, comfrey. Medicinal plants: ground cover, strawberries, clover, oregano. Rhizosphere: potatoes, turmeric, ginger, sunchokes. Vines: grapes, kiwi, passion fruit. Key principle: a food forest produces harvest in all seasons because some layers fruit in every part of the year. Seasonal productivity master plan: spring, rebirth and rapid growth. Early fruit trees bloom: peaches, plums, apricots. Early greens: spinach, arugula, lettuce, mustard. Root crops: radish, beet, carrot. Perennials: asparagus, rhubarb, artichokes. Boosting resilience: use floating row covers to extend early growth. Add compost teas to accelerate soil biology. Summer, peak harvest and abundance: tomatoes, corn, beans, cucumbers, peppers, berries, raspberry, blackberry, currants. Tree fruit: apples, pears, figs, mulberries. Mediterranean herbs: basil, thyme, lavender. Summer resilience: deep mulch, shade-tolerant varieties. High-carbon compost to retain water. Autumn, storage crops and long-term resilience: squash, pumpkins, sweet potatoes, nuts, walnuts, hazelnuts, chestnuts. Late apples, pears, kale, collards. Continue into winter. Autumn strategy: plant cover crops immediately after harvest. Build new ecological beds using fall wood. Winter, cold season production. With proper design, winter is not dead time. Winter producers: cold frames for spinach, lettuce, kale, perennial greens, miner's lettuce, claytonia, sorrel, mushrooms in logs or shaded beds. Evergreen herbs: rosemary, sage. Indoor microgreens. Winter resilience: greenhouses with thermal mass. South-facing wall gardens. Mulch vegetable beds heavily. Use perennial staple crops for year-round security. These crops ensure permanent, reliable food without replanting. Carbohydrates: sunchokes, Jerusalem artichokes, perennial potatoes, Apius americana, yacon. Chestnuts, grain replacement. Acorns, after leaching. Breadfruit, tropics, bamboo shoots. Proteins: pigeon pea. Tree collards, perennial beans, moringa leaves. Nuts: walnut, hazelnut, pecan. Fats: avocado, nuts, olives, coconut. These crops offer food during winters, droughts, and disasters. Integrate animals for maximum fertility and maintenance. Animals turn waste into fertility and keep the ecosystem self-regulating. Chickens pest control. Constant manure for compost. Scratch until mulch layers. Duck, snail and slug control. Excellent in wet areas. Goats and sheep brush clearing. Maintain fruit tree understory. Bees pollination boosts productivity everywhere. Outcome, a fully functional, fertilizing ecosystem. Integration systems for maximum productivity. Culture mounds break down wood to release nutrients for 20 years. Excellent for year-round water retention. Forest garden guilds examples: apple plus comfort plus clover plus garlic plus daikon radish, peach plus lavender plus thyme plus grapes. Polyculture beds never grow. A monoculture, mix species to boost resilience. Biointensive beds, densely planted beds maximize space and reduce weeds. Create a year-round harvest calendar. This ensures there is always something to pick. Winter kale, collards, overwintering broccoli, spinach, miner's lettuce, winter roots stored in ground, carrots, beets, spring asparagus, rhubarb, lettuce, early peas, strawberries, summer tomatoes, melons, cucumbers, most berries, stone fruits, autumn pumpkins, squash, apples, pears, hardy kiwis, nuts. Make the system fully regenerative to achieve long-term resilience. Plant nitrogen-fixing trees, acacia, alder, locust. Use chop and drop mulching from fast-growing shrubs. Feed soil fungi with woody mulch. Limit soil disturbance to protect carbon. Rotate animals through paddocks for natural fertilization. Keep water on the land. Build biodiversity across plants, insects, and microbes. Designed for climate change and extreme weather. Storms, deep-rooted perennials and food forests reduce damage. Drought, shade, mulch, swales, and perennials maintain moisture. Heatwaves, multi-layer canopy regulates temperature. Floods, terracing and water flow control prevent erosion. Cold snaps, thermal mass and evergreen windbreaks protect crops. A permaculture system is self-adapting, not fragile. A hyper-productive, hyper-resilient, year-round food ecosystem. By following this blueprint, you create a system that produces food in every season, survives heat, drought, cold, storms, restores biodiversity, regenerates soil automatically, supports wildlife, captures carbon, eliminates dependence on external inputs, becomes more productive every single year. It is essentially building a small-scale Eden that serves both people and nature. Comprehensive explanation: how to create the most productive and resilient permaculture for every season of harvest. Creating the most productive and resilient permaculture system for year-round harvest requires designing an ecosystem that can sustain itself through all seasons, climate stresses, and changes in environmental conditions. This is achieved by building interconnected cycles of soil fertility, water retention, plant diversity, animal integration, and microclimate management. A highly functional permaculture system behaves like a natural forest. It is self-maintaining, biologically rich, and capable of producing food continuously without the need for constant human intervention. By designing such a system, seasonal limitations disappear, and productivity becomes embedded in the landscape year-round. A successful year-round permaculture system begins with building healthy soil, because soil is the foundation upon which all resilience depends. Fertile soil contains abundant microorganisms, earthworms, fungi, and organic matter that work together to retain moisture, store nutrients, and support plant growth throughout the year. To create this type of soil, gardeners use deep organic mulches such as straw, leaves, or wood chips, which gradually decompose and feed the soil food web. Compost, biochar enriched with nutrients, and perennial root systems also help create long-lasting soil fertility. By avoiding tilling, the system preserves soil structure and fungal networks that regulate moisture and deliver nutrients even in harsh conditions. When soil becomes a living sponge, plants thrive in all seasons. Water management is the next essential component of multi-season resilience. A productive permaculture system captures rain where it falls, slows it down, and sinks it into the ground so the land remains moist even during dry months. This is done by shaping the landscape with water harvesting features such as swales on contour, small ponds, terraces, rain gardens, and hollows where water can accumulate naturally. The system also uses gray water from households and low-pressure irrigation, such as drip lines and clayos, to deliver moisture directly to plant roots. Combined with thick mulch and strategic shade created by trees, these techniques drastically reduce evaporation and ensure that soil remains hydrated through heatwaves, droughts, and dry seasons. When water is retained in the landscape, crop production becomes stable year-round. To maintain productivity during temperature extremes, permaculture designs incorporate microclimate engineering. Windbreaks made of trees or shrubs reduce cold winter winds and create sheltered warm pockets where more sensitive plants can grow. Sun traps, rock walls, and thermal mass structures absorb heat during the day and release it at night, making it possible to grow food even during cold seasons. Shade trees, trellises, and layered plant canopies cool the land during summer and protect heat-sensitive crops from sun stress. With the proper arrangement of plants and landscape features, the land becomes a network of microhabitats where different species can thrive regardless of seasonal weather conditions. As a result, food production becomes less dependent on the external climate and more reliant on the designed environmental conditions. A highly productive permaculture system functions most effectively when it uses the structure of a food forest, which consists of multiple layers of vegetation working together like a natural woodland. These layers include a canopy of large fruit or nut trees, a subcanopy of medium-sized trees, a shrub layer of berries, an herb layer of culinary and medicinal plants, a ground cover layer that protects soil, a root layer that stores food underground, and a vertical layer of climbing vines. This multi-layered structure captures sunlight from every angle, reduces competition, builds biodiversity, and creates continuous harvest cycles because different species fruit at different times of the year. When one crop finishes, another begins, creating a perpetual chain of productivity. Year-round harvesting is achieved by planting species that peak during different seasons. Spring growth is dominated by early greens, perennial sprouts, berries, and early fruit trees. Summer produces abundant vegetables, fruits, herbs, and annual crops. Autumn provides storage crops such as squash, potatoes, nuts, and late-season fruit. Winter production continues through cold hardy greens, protected garden beds, greenhouse crops, mushroom logs, and perennial species adapted to cool temperatures. With proper planning, each season overlaps with the next, ensuring that food is always available. Perennial staple crops form the backbone of the system's long-term resilience. Perennial vegetables, roots, nuts, and trees produce food year after year without needing replanting, which reduces labor, builds soil, and maintains continuous nutrient cycles. These crops are better adapted to seasonal fluctuations, and their deep roots access water and minerals even during droughts or cold spells. By incorporating perennial beans, leafy greens, oil-producing nuts, carbohydrate-rich tubers, and fruit-bearing shrubs, the system becomes increasingly productive over time. Animal integration enhances both fertility and resilience. Chickens, ducks, goats, bees, and fish in ponds play ecological roles that support plant growth. Chickens control pests, produce eggs, and provide nutrient-rich manure. Ducks thrive in wetter areas and are excellent slug and snail predators. Goats and sheep maintain understory vegetation, produce milk and fiber, and promote nutrient cycling. Bees pollinate fruiting plants and increase yields. Fish in aquaponic systems or natural ponds convert food waste into fertilizer-rich water that boosts plant growth. Animals function as living workers within the system, constantly renewing fertility and closing nutrient loops. The integration of soil-building practices, plant diversity, animal activities, and water retention gradually transforms the landscape into a self-sustaining ecosystem. As organic matter accumulates, soil deepens and becomes increasingly capable of retaining moisture and nutrients. As trees mature, they create shade, stabilize temperatures, and anchor the water cycle. As biodiversity increases, pests become naturally controlled by predator insects and birds. Over time, the system becomes more productive and resilient, requiring fewer external inputs each year. A year-round permaculture system is also designed to withstand the impacts of climate change. Deep-rooted perennials, layered canopy structures, and water harvesting landscapes stabilize ecosystems during droughts, storms, heat waves, floods, and cold snaps. The system's diversity ensures that even if some species fail in a particular season, others will continue producing. Microclimates buffer temperature extremes, and long-term soil fertility protects against crop failure during environmental stress. As a result, the land becomes increasingly adapted to climatic unpredictability. In conclusion, creating the most productive and resilient permaculture system for every season requires designing a self-sustaining ecosystem that prioritizes healthy soil, efficient water management, plant diversity, perennial crops, strategic microclimate engineering, and animal integration. By emulating the structure and functions of a natural forest, the permaculture system becomes capable of producing food continuously, regenerating its own fertility, and withstanding environmental challenges throughout the entire year. This approach transforms the land into a regenerative, abundant, and climate-resilient food-producing environment that becomes richer and more productive with every passing season. What's the most regenerative and productive agroforestry design for every month of harvest? Here is an explanation of the most regenerative, productive, year-round agroforestry design that provides harvest every single month of the year in a stable, self-renewing way. This describes a system that works in temperate, subtropical, and tropical climates by adjusting species, but the design principles are universal. The most regenerative and productive agroforestry design for continuous, year-round harvest. A year-round agroforestry system must function like a highly complex ecological engine, combining trees, shrubs, vines, groundcovers, root crops, fungi, and animals into a multi-layered living architecture. This architecture captures sunlight at all heights, retains moisture, builds soil, and maintains biological activity throughout all seasons. The key principle is diversity across both vertical layers and seasonal rhythms, so that as one species finishes producing, another begins, forming a seamless calendar of productivity. The most regenerative and productive agroforestry design for year-round harvest is a climate-adapted food forest organized into zones, layers, and phenological, seasonal, cycles, supported by water harvesting, living soil, and animal integration. This design produces food, fiber, fuel, medicine, building materials, and ecological services every month of the year. The core structure, a multi-layered perennial food forest. The backbone of continuous monthly harvest comes from building a 7-layer food forest, which includes a tall canopy of nut and fruit trees, a mid-story of smaller fruit trees, a shrub layer of berries and nitrogen fixers, an herbaceous layer of vegetables, medicinals, and pollinator plants, a ground cover layer for soil cover and moisture retention, a root zone layer of perennial tubers, a vertical layer of vines for fruit and biomass. Because each layer contains species that fruit or mature in different months, the forest becomes a self-regulating calendar of production. Harvesting and microclimate engineering. Monthly productivity is impossible without stable water and climate buffers. A regenerative agroforestry system uses swales and terraces to slow and absorb rainfall, ponds and seasonal wetlands to store water, windbreaks and shelter belts to control temperature extremes, sun traps and thermal mass to allow crops to grow through cold periods, shade canopies to protect cool season crops during hot months. By regulating temperature and moisture, this system allows fruiting and growth even through seasonal stress. Soil as a living sponge. A year-round productive agroforestry design depends on soil that remains biologically active in all seasons. This is achieved by permanent mulches, continuous root living systems, nitrogen-fixing trees and shrubs, mycorrhizal networks, biochar enriched with compost, leaf litter cycling from multi-layer canopies, animal manure inputs. The soil becomes a resilient engine that retains moisture, cycles nutrients, and produces harvest even in winter or drought. Monthly harvest structure, a year-round phenological design. Here is the ideal structure for a system that produces across all 12 months. Local species will differ, but the pattern is universal. January, winter greens, stored roots, winter fruits. A well-designed agroforestry system includes cold hardy greens, evergreen species, winter citrus, in mild climates, storage roots left in the ground, mushrooms in wood beds, and nits stored from autumn. February, late winter greens, sap, early citrus. Winter hardy perennials, maple sap, in cold climates, late winter citrus, and overwintering brassicas provide February harvests. March, early spring shoots, herbs, early blossoms as temperatures rise, edible shoots, herbs, asparagus, rhubarb, early berries, and spring tree crops begin producing. April, spring fruits, leafy greens, early berries, strawberries, mulberries, spring apples and plums, early peas, and fast-growing herbs become abundant. May, full spring production. Spring vegetables, small fruits, early summer fruits, medicinal herbs, and the first flush of temperate grains mature. June, early summer fruits and vegetables. Cherries, gooseberries, raspberries, currants, early peaches, the first melons, and dense green vegetation appear. July, peak summer production. Tomatoes, summer berries, nectarines, figs, beans, grapes, and tropical tender crops, in protected microclimates, reach full abundance. August, storage crops and late summer fruits. Late peaches, pears, grapes, squash, beans for drying, maize, and the fullest canopy. Biomassacre. September, early autumn staple crops. Apples, pears, hazelnuts, chestnuts, pumpkins, sweet potatoes, and late berries mature. October, autumn protein and carbohydrate month, nut harvest peaks, late apples, persimmons, tubers, late grapes, and overwintering greens begin. November, root and perennial leaf crops, roots, brassicas, cold season greens, pomegranates, olives, and late nuts complete the late autumn season. December, winter fruits, citrus, persimmons, greens, and mushrooms, cold hardy greens, stored nuts, winter citrus, and sheltered perennial crops provide December harvests. Designing plant guilds that mature in staggered monthly cycles guarantees constant productivity. The most regenerative agroforestry layout, a monthly harvest food forest. Plant these near the home: perennial vegetables, culinary herbs, orchard trees with monthly fruiting sequences, mushroom beds, chickens for fertility and pest control. Zone 2, intensively managed mixed agroforest, fruit and nut trees arranged in a succession timeline. Shrubs arranged by monthly fruiting, year-round greens and microclimates, aquaponics or pond systems. Zone 3, staple crop agroforest, chestnuts, pecans, walnuts, hazelnuts, perennial tuber beds, protein-rich perennial legumes, timber and biomass trees. Zone 4, woodland regeneration zone, nitrogen fixers, wildlife habitat, bees. Zone 5, wild zone, biodiversity reservoir, climate buffering forest. This zoning ensures that every layer in every month is productive while maintaining ecological integrity. Key ecological mechanisms that enable monthly harvest. A monthly harvest system is only possible because of phenological diversity, plants fruit in different months, vertical diversity, multi-layered canopies, perennial dominance, continuous root activity, successional layers, pioneer mid-succession climax species, microclimate fabrication, windbreaks, shade, thermal mass, hydrological stability, swales, ponds, terraces, animal-plant nutrient cycling. The system becomes more productive and regenerative every year, rather than degrading like industrial agriculture. Result, a hyperproductive, self-regenerating, monthly output ecosystem. When designed correctly, a regenerative agroforestry system produces food every month of the year, builds soil instead of depleting it, regulates water naturally, protects itself from drought, heat, cold, and storms, creates habitat for pollinators and wildlife, stores carbon and biomass in soil, provides fruits, nuts, tubers, vegetables, herbs, mushrooms, and animal products, increases yields as it matures, requires less labor over time. This is the closest human-designed system to a fully regenerative, edible natural forest that functions reliably in every season. The most regenerative and productive agroforestry designed for monthly harvests. A complete explanation. Designing an agroforestry system that reliably yields harvests every month of the year requires thinking of the land as a temporal and vertical tapestry rather than as isolated annual crops. A truly regenerative, productive agroforestry design begins by creating a living matrix of perennial and annual plants, animals, water infrastructure, and soil biology that interact continuously. When these components are arranged intentionally for staggered phenology and layered sunlight capture, the landscape itself becomes a month-by-month producer. The aim of this design is to build soil and store water, to spread risk across many species and ages of plants, and to fabricate microclimates that extend growing seasons so that there is something to harvest in every month. The foundation of the system is living soil, because soil is where resilience and productivity originate. Healthy soil contains stable organic matter, abundant microbial and fungal networks, and a dense, permanent root web. To create this soil, I recommend establishing permanent mulches, heavy volumes of compost and compost teas, and the integration of deep-rooted perennials and nitrogen-fixing trees that feed the soil through leaf litter and root exudates. Avoiding repeated tillage preserves soil structure and the fungal hyphae that shuttle nutrients and water to plants, and adding biochar or wood-based carbon helps the soil hold nutrients and moisture over seasons. When the soil functions as a living sponge, plants experience less stress during heat and drought and continue to produce through marginal months. Equally important is hydrological design aimed at keeping water on the property year-round. This starts with simple earthworks, such as swales on contour, terraces, ponds, infiltration basins, and channels that slow runoff and allow rain to sink into the ground. These features should be placed where they recharge root zones of key perennial crops and where stored water can be accessed for irrigation in dry months. Mulch, ground cover, and tree canopies reduce evaporation losses, and graywater and roof water capture systems can be reused to irrigate high-value beds. When water is managed to sink and spread rather than to run away, the system can sustain production across both wet and dry months. The agroforestry layout must deliberately layer plants vertically and sequence them temporally. A 7-layer food forest model, consisting of canopy trees, sub-canopy trees, shrubs, herbaceous plants, groundcovers, root crops, and vines, captures light and productive niche space at every height. Each layer should be populated with species that have staggered fruiting and harvest times so that the whole system's phenology is distributed across months rather than concentrated in one season. For example, early producing shrubs, spring blooming trees, summer bearing vines, autumnal nuts and pears, and overwintering greens combined across the landscape create overlapping harvest windows. Designing guilds, small plant communities built around a support tree that include nitrogen fixers, dynamic accumulators, pollinator plants, insectary strips, and ground covers, ensures each tree is supported by a local nutrient and pest management network. Resilience comes from diversity and redundancy. Planting a wide range of species, genetic varieties, and ages reduces risk from pests, diseases, and climate anomalies. Some species will fail in a particular month or year, but the presence of other species producing at the same time buffers that loss. Perennial staples, such as nut trees, fruit trees, perennial legumes, and tuberous plants, provide continuity because they require less replanting and because their deep roots access water and nutrients during stress periods. Annuals and fast-cycling shrubs provide high-intensity harvest for limited months and can be rotated into gaps created by harvesting or coppicing. Microclimate engineering extends and stabilizes monthly production. Windbreaks and shelter belts reduce desiccating winds and lower winter heat loss, while sun traps, thermal mass walls, and south-facing terraces capture sunlight and moderate nighttime temperature drops. Shade trees and layered canopies protect cool season crops from summer heat and allow tender species to persist in otherwise marginal months. Small-scale greenhouse structures, cloches, cold frames, and mulched roots can push the productive window of herbs, greens, and saplings into months that would otherwise be off-season. Animals are an integral component of a regenerative monthly production system because they close nutrient loops and provide products during months when plant yields are lower. Poultry provides eggs and fertility and can be rotated through orchard floors to recycle fallen fruit, while ducks do especially well in wetter orchard corners and control snails and slugs. Managed bees increase fruit set and early season yields, and small ruminants can be used carefully for understory management and pruning residues. Aquatic systems such as ponds with fish or integrated aquaponics provide protein and nutrient-rich water that can be directed to produce beds in drier months. A month-by-month harvest calendar should be created at the outset to ensure phenological coverage. This calendar must be localized to the site's climate and should pair long-term perennials that provide staples across many months with opportunistic annuals and microclimate-enhanced beds that fill gaps. In practice, January and February harvest can come from winter greens, stored roots, nut caches, bee products, and protected greenhouse crops. March through May pulse with early greens, asparagus, peas, berries, and early tree fruits. June to August deliver peak annual and tree fruit production with tomatoes, cucurbits, stone fruits, and berries. September and October bring apples, grapes, nuts, and root crops for storage, while November and December supply cold hardy leafy vegetables, late citrus or persimmons in mild zones, and mushroom logs. This continuous overlap is achieved by selecting species and cultivars that mature at different times, and by placing those species in microclimates that nudge their phenology earlier or later, as needed. Maintenance in such a system focuses on nurturing the ecological processes rather than on intensive inputs. Yearly tasks include plant coppicing and pollarding for biomass, targeted pruning to balance light distribution, periodic planting of nitrogen fixers and dynamic accumulators to maintain fertility, seasonal mulching to rebuild cover, and monitoring for pest outbreaks so that biological controls can be encouraged rather than chemicals applied. Record keeping of yields, pest incidences, and microclimate performance helps refine species choices and placement over time. Finally, the regenerative and productive agroforestry design is dynamic and adaptive. It intentionally accommodates succession, allowing pioneer species to give way to longer-lived trees while maintaining understory cycles that are constantly renewed. As the system matures, soil depth increases, water holding capacity improves, and microclimates stabilize, which in turn lengthens productive months and raises total yield. When designed with layered structure, phenological diversity, water capture, living soil, animal integration, and microclimate engineering, an agroforestry landscape becomes a self-regulating calendar of harvest that produces usable food and materials in every month while increasing ecological health year after year. Designing the most regenerative and productive agroforestry system for year-round harvest. Agroforestry represents one of the most powerful methods for creating food systems that are simultaneously productive, resilient, ecologically regenerative, and climate adaptive. By intelligently combining trees, shrubs, vines, root crops, annual vegetables, perennial foods, and livestock in an integrated structure, agroforestry can produce a continuous stream of food and resources in every month of the year. To achieve year-round harvests, the system must be designed as a living mosaic of microclimates, ecological layers, complementary species, and nutrient cycles. This essay provides a comprehensive explanation of how to design such an agroforestry system, why it works ecologically, and how to maintain production and regeneration in every season. Principles of designing a year-round agroforestry system. Agroforestry excels when it integrates ecological processes with human needs. The most productive and regenerative systems are built on the following principles. Layered vertical diversity. A multi-layered structure ensures production at all heights and creates a self-stabilizing ecosystem. The 7 layers include canopy trees, fruit, nut, timber, subcanopy trees, medium fruits, nitrogen fixers, shrubs, berries, medicinal plants, herbaceous layer, vegetables, culinary herbs, groundcover, strawberries, clover, rhizosphere, root crops, vines, grapes, kiwis, passion fruit. These layers increase productivity without increasing land area, similar to natural forests. Polyculture instead of monoculture. Diverse guilds of plants reduce pest pressure, stabilize soil, fill ecological niches, and balance nutrient demands and inputs. Regenerative soil building. Healthy soil determines long-term productivity. Agroforestry systems enhance soil life by using deep-rooted perennials to pull nutrients upward, applying mulch, compost, and biochar, maintaining constant ground cover, encouraging fungal networks, mycorrhizae, supporting nitrogen-fixing species. Microclimate creation. Trees and shrubs modify wind, shade, humidity, and temperature. This allows winter protection for cold-sensitive plants, extended autumn and spring growing periods, summertime moderation of heat stress, reduced drought vulnerability, water cycling and hydration. Water is retained and recycled through swales, ponds, contour trenches, tree root systems, dense mulch layers, vegetated cover to reduce evaporation. This increases resilience in dry seasons. Perennial dominance with strategic annual integration. Annuals provide quick yields, while perennials provide long-term stability, nutrient cycles, and structural resilience. Continuous bloom, fruit, and seed cycles to support pollinators and maintain yield every month. The system must always include plants that are blooming, fruiting, leafing, setting seed. Structural layout for a regenerative year-round agroforestry system. Windbreaks and shelter belts. These are planted along the perimeter to reduce wind, prevent erosion, trap snow, and create a warmer microclimate. They often include pines, spruces, alders, mulberries, willow, bamboo, caragana. Food forest backbone. Within the shelter belts, the food forest forms the main body of the system. It should include tall canopy rose, pecans, chestnuts, walnuts, subcanopy fruit trees, apples, peaches, persimmons, nitrogen fixers, acacia, black locust, seaberry, shrub rose, currants, blueberries, elderberries, ground cover beds, strawberries, clover, creeping thyme, herbaceous strips, comfrey, calendula, basil, onions. Contour-based water management across sloped land, swales and terraces capture rainwater and hydrate tree root zones. On flat land, keyline patterns optimize infiltration. Alley cropping zones. Wide alleys between tree rows allow grains, vegetables, flowers, fodder crops, mushrooms, in shade zones. Animal integration. Animals create fertility and regulate pests, chickens, insect control, ground cover management, ducks, slug control, aquatic integration, goats, sheep, understory grazing if managed carefully, bees, pollination, woodland edges and aquatic systems. Ponds and wetlands produce fish, water plants, cranberries, irrigation water, microclimate moderation, monthly harvest design, ensuring year-round food production. Below is an integrated system showing how regenerative agroforestry project can produce crops in every month of the year. Winter, cold season productivity. Winter harvests rely on hardy perennials, storage crops, and microclimates. Harvests include kale, collards, chard, leeks, onions, garlic, Jerusalem artichokes, carrots and beets in cold frames, winter berries, sea buckthorn, rosehips, mushrooms grown in sheltered shade, nuts stored from autumn, pecans, walnuts, chestnuts. Design strategies: use cold frames, greenhouses, and south-facing walls for heat. Plant cold-hardy evergreen herbs, rosemary, thyme. Use windbreaks to prevent tree stress and soil cooling. Early spring, waking system with early foods harvests include asparagus, ramps, wild onions, dandelion greens, early radishes, spring peas, nettles, mint shoots, overwintered brassicas, early apricots in warm climates. Late spring, high diversity begins. Harvests include strawberries, cherries, mulberries, early apples, rhubarb, lettuce, kale, spinach, herbs, basil, parsley, cilantro, edible flowers. Spring is also the peak time for pollinator-supported growth. Summer, intensive production. This is the season of maximum sun, heat, and fruit set. Harvests include peaches, plums, nectarines, grapes, hardy kiwis, tomatoes, peppers, eggplants, corn, squash, beans, berries, raspberries, blueberries, blackberries. Herbs for drying. Microclimates keep heat stress low and irrigation needs manageable. Autumn, storage and long-term yield season. Autumn is the backbone of year-round food security. Harvests include apples, pears, persimmons, figs, in warm climates, pumpkins in winter, squash, sweet potatoes, hazelnuts, pecans, walnuts, chestnuts, late raspberries, grapes, medicinal herbs and roots. Perennial roots deepen, nutrient storage increases, and soils are enriched by falling leaves. Ecological processes that make agroforestry regenerative. Nutrient cycling: trees pull minerals from deep layers and drop them as leaf litter. Soil organisms transform that litter into plant-available nutrients, making the system self-fertilizing. Biodiversity increases stability. Diverse species prevent pest outbreaks, reduce disease spread, and support beneficial insects and birds. Carbon sequestration: trees and perennial roots capture and store carbon, improving soil structure and reversing degradation. Water retention: root systems and mulches build organic matter that holds water like a sponge, stabilizing production even during droughts. Continuous photosynthesis: a well-designed agroforestry system keeps green photosynthetic surfaces active in every season, ensuring constant ecosystem metabolism. Management strategies for maximum regeneration and productivity: mulching: maintain 5-10 centimeters of organic mulch around all plantings to reduce evaporation, support fungi, feed soil invertebrates, suppress weeds. Moderate temperature: chop and drop cutback nitrogen fixing shrubs and herbaceous plants and leave them as mulch, recycling nutrients on site. Pruning and training: proper pruning increases sunlight penetration, reduces disease, and extends productive lifespans. Integrated pest management: attract predators, ladybugs, lacewings, birds, frogs, bats. Avoid chemicals to preserve ecological balance. Succession planning: young plantings coexist with fast-growing pioneer species. Over time, long-lived perennials replace pioneers. The blueprint for a year-round regenerative agroforestry system. A regenerative, highly productive agroforestry design is essentially a cultivated forest that operates like a natural ecosystem but yields abundant food year-round. By integrating layered plant structures, animal systems, hydrological design, microclimates, perennial soil builders, and robust ecological cycles, it becomes possible to harvest in every month of the year while steadily improving the land. This system not only provides consistent food but also restores degraded soils, rebuilds biodiversity, supports pollinators, stabilizes water cycles, and captures carbon. It represents one of the most powerful solutions for sustainable resilience, ecological restoration, climate adaptation, and global food system transformation. How can we solve the world's sustainability, pollution, inequity, economic and other problems with permaculture and agroforestry systems? How permaculture and agroforestry can solve sustainability, pollution, inequity, economic, and related global problems. Permaculture and agroforestry are place-based design systems that mimic natural ecosystems to produce food, materials, energy, and ecosystem services. When implemented at scale and supported by appropriate policies, markets, finance, and social programs, these systems can lift environmental performance, reduce pollution, restore degraded lands, build equitable livelihoods, and make local and global economies more resilient. The paragraphs below explain, in clear and complete sentences, the mechanisms by which permaculture and agroforestry address specific problems, how to scale them, what policies and institutions are needed, and what challenges must be managed. How these systems improve ecological sustainability. Permaculture and agroforestry rebuild ecological functions that industrial systems often destroy. By emphasizing perennial plants, multilayered vegetation, continuous ground cover, and living roots, they increase soil organic matter, expand soil microbial and fungal networks, and increase water infiltration and retention. These changes reduce erosion, increase drought resilience, and make landscapes more productive per unit of rainfall and sunlight. Trees and perennial biomass sequester carbon above and below ground, which contributes to climate mitigation while improving microclimates for crops and people. In short, permaculture and agroforestry transform degraded, input-hungry farmland into productive, water-wise, carbon-storing ecosystems. How they reduce pollution and restore ecosystems. Permaculture and agroforestry minimize or eliminate synthetic agrochemical use by relying on biological pest control, polycultures, and soil health. Reduced fertilizer runoff and pesticide drift directly lower waterway eutrophication, dead zones, and human exposure to toxic chemicals. Riparian buffers, hedgerows, and tree belts filter sediments and nutrients before they reach streams, and deeply rooted perennials stabilize soils and reduce particulate pollution. Additionally, by replacing monoculture clearing with integrated tree cover, these systems restore habitat, increase biodiversity, and reconnect fragmented ecosystems, which improves pollination, biocontrol, and ecological stability. How they address inequity and build livelihoods. Permaculture and agroforestry create diversified income streams for smallholders and communities by producing food, fodder, timber, fiber, medicine, fuelwood, and value-added products such as oils, preserves, and handicrafts. Because these systems rely more on local knowledge, labor, and biological inputs than on expensive external inputs, they lower entry costs for marginalized farmers and enable more stable, resilient incomes. Cooperative processing, community nurseries, and local markets amplify earning potential and keep value in communities. Women, indigenous peoples, and youth can gain secure livelihoods through nursery work, value-added processing, and stewardship roles, which helps reduce inequality and strengthen social capital. How they strengthen local and regional economies. Agroecological systems circulate wealth locally by relying on local labor, seed systems, and small-scale processing. This reduces dependency on imported inputs and long supply chains, making rural economies more self-reliant and less vulnerable to global shocks. Localized food systems shorten transport distances, lower greenhouse gas emissions from logistics, and expand jobs in processing, distribution, and retail within communities. Over time, healthy landscapes increase property values, tourism potential, and ecosystem service payments that can be reinvested into local infrastructure and social programs. How they increase food security and nutritional outcomes. Permaculture and agroforestry emphasize dietary diversity by integrating fruits, vegetables, legumes, nuts, tubers, leafy greens, and protein sources into the same landscape. This diversity grows year-round food availability and decreases seasonal hunger gaps. Perennial and polycultural systems also reduce post-harvest losses by providing multiple harvest windows and storage crops that are more resilient to climate variability. By improving soil fertility and microclimates, these systems raise yields of nutrient-rich foods and reduce reliance on single staple crops, which improves population health and nutritional security. How they create climate resilience and disaster risk reduction. The structural complexity of agroforestry systems buffers farms against extremes. Tree canopies reduce wind and solar stress on understory crops, root networks stabilize slopes and reduce landslides, and increased soil organic matter acts as a buffer against both drought and flood by improving infiltration and water retention. Wetland and pond elements attenuate flood peaks and store water for dry seasons. At landscape scale, mosaics of agroforestry, repair and restoration, and rewilding reduce the severity of fires and protect watersheds, which lowers community vulnerability to climate-related disasters. How they contribute to carbon sequestration and ecosystem service markets. Because trees and long-lived perennials store carbon in biomass and soil, agroforestry systems can deliver measurable carbon sequestration. When combined with robust measurement, reporting, and verification, MRV, Systems and fair benefit sharing mechanisms, carbon payments and ecosystem service markets can finance adoption and maintenance. Co-benefits such as biodiversity, water regulation, and soil health increase the value of such payments and create multiple revenue streams for land stewards. Policy, governance, and finance pathways to scale impact. Scaling permaculture and agroforestry requires aligned public policy, accessible finance, and capacity building. Land tenure security is essential because trees represent long-term investments. Secure rights enable farmers to adopt perennial systems. Subsidy reform is necessary so that public funds favor regenerative practices rather than chemical-intensive monocultures. Technical extension services, farmer-to-farmer networks, and demonstration sites accelerate knowledge diffusion. Financial instruments such as low-interest green loans, blended finance, outcome-based payments, and carbon or ecosystem service credits make upfront establishment costs feasible. Policies that support local processing, value chains, and equitable benefit sharing help ensure that financial gains remain local. Technology, research, and measurement to improve outcomes. Agronomic research, plant breeding for perennial or multipurpose species, and practical MRV methods help optimize yields, resilience, and carbon accounting. Digital tools can map landscapes, model water flows, and match species to microclimates. However, these technologies should complement and amplify local knowledge, not replace it. Participatory monitoring that includes community data keeps management adaptive, equitable, and locally relevant. Social and cultural dimensions, education, rights, and stewardship. Real transformation requires cultural change in education. Integrating permaculture and agroforestry into school curricula, vocational training, and community workshops builds the human capital to design, install, and manage these landscapes. Recognizing and protecting indigenous land rights, traditional ecological knowledge, and community governance models ensures ethical implementation and leverages generations of place-based wisdom. Social safety nets, cooperative ownership models, and revenue-sharing agreements prevent elite capture and ensure broad-based benefits. What a global transition could look like in practice. A credible transition would combine bottom-up adoption and top-down enablement. At the local level, thousands of community nurseries, demonstration farms, and agroecology training centers would help restore degraded lands, diversify livelihoods, and pilot finance models. At national and international levels, governments and multilateral institutions would redirect subsidies, invest in rural infrastructure, and create transparent marketplaces for ecosystem services. Public procurement, for schools, hospitals, and government institutions could preferentially buy from regenerative producers, creating demand. International climate finance and development assistance would prioritize landscape restoration and equitable benefit sharing to accelerate adoption in low-income regions. Potential challenges and mitigations. There are technical, institutional, and social challenges to scaling these systems. Short-term yield expectations, lack of tenure, cultural inertia, and misaligned market incentives can slow adoption. To mitigate these problems, programs can include transitional income support, secure long-term land agreements, phased adoption strategies that combine annual and perennial production, and targeted market development for value-added products. Strong monitoring, transparent governance, and inclusive stakeholder processes reduce risks of inequitable outcomes. Metrics for success. Success should be measured across environmental, social, and economic dimensions. Key indicators include soil carbon and organic matter, water infiltration rates, biodiversity indices, household income stability, food diversity and nutritional status, land tenure security, and participation rates of marginalized groups. Tracking these indicators at landscape and community scales allows adaptive management and ensures that interventions meet both ecological and social goals. A practical roadmap for implementation. A practical roadmap begins with pilot landscapes and scales through networks. The steps include secure land and tenure arrangements, establish nurseries and seed systems, co-design sites with communities using participatory mapping, implement water harvesting and soil building measures, plant mixed species, multi-layered systems, integrate animals and establish local processing, create cooperative market channels, set up MRV for ecosystem services, and design finance and policy supports that reward long-term stewardship. Iterative learning and adaptive management accelerate progress while protecting livelihoods. Systemic benefits. In the moral case, permaculture and agroforestry present a systemic alternative to extractive, polluting, and inequitable agricultural models. By regenerating soils, restoring water cycles, sequestering carbon, diversifying livelihoods, and strengthening local economies. These systems address multiple crises at once. When policies, finance, research, and cultural support align, permaculture and agroforestry can become foundational tools for a just and sustainable transition. They do not offer a quick fix, but they do offer durable pathways to heal landscapes, empower communities, and redesign economies in ways that prioritize ecological integrity and human well-being. How can this replace most industries and increase sustainability in many ways? Here is a clear, detailed, and comprehensive explanation of how permaculture and agroforestry can replace most destructive industries, decentralize production, and dramatically increase global sustainability. The key point is not that they eliminate all industries, but that they replace the most wasteful, extractive, polluting, and resource-intensive ones with regenerative, bio-based, circular, community-empowering systems. How permaculture and agroforestry can replace most industries and dramatically increase sustainability. Permaculture and agroforestry can substitute for many industrial sectors because they produce food, materials, energy, chemicals, medicine, textiles, construction resources, and ecosystem services directly from living landscapes. Instead of massive factories, global shipping, mines, oil wells, and chemical plants, they use soil biology, plant diversity, natural cycles, and renewable sunlight to manufacture what society needs. This transformation lowers environmental impacts, strengthens local economies, and stabilizes the climate. Below is a sector-by-sector breakdown of how this works. Replacing the industrial food system. Industrial agriculture relies on monocultures, chemical fertilizers, diesel, pesticides, and long supply chains. Permaculture and agroforestry replace them with local, self-renewing food forests, which serve as decentralized biological factories. Agroforestry can replace synthetic fertilizer production via nitrogen, fixing trees and nutrient cycling, pesticide manufacturing via biodiversity, predator habitats, and polycultures, industrial grain and vegetable farms via perennial staple crops, nut trees, tubers, fruit shrubs, edible groundcovers, animal feed factories via silvopasture, forage trees, and fodder hedgerows, chemical soil amendments via compost, mulch, biochar, and fungal networks. This shift reduces CO2 emissions, soil loss, water pollution, and supply chain risks, replacing the oil, gas, and fossil fuel industries. Many fossil fuel functions can be replaced by biological systems that produce energy and materials. Permaculture agroforestry can produce bioenergy, wood, coppice fuel, bamboo pellets, biogas, bio-oils, bioplastics from starch, cellulose, and plant oils, natural rubber from trees, charcoal and biochar for energy and soil enhancement, cooling functions through shelter belts instead of air conditioning demand. While they cannot replace all fossil fuels immediately, they dramatically reduce dependence by improving efficiency and creating renewable on-site sources. Replacing the timber and construction industries. Agroforestry can produce immense volumes of renewable construction material without clear-cutting forests. Replacements include bamboo for flooring, scaffolding, panels, composites, fast-growing timber species grown in polyculture, living fences and windbreaks instead of concrete walls, coppiced wood for long-term, regenerative yielding, hemp, flax, and mycelium-based building materials, straw bale, earth plasters, and natural insulation. Regenerative forestry eliminates deforestation, reduces carbon emissions, and produces stronger local supply chains. Replacing the chemical industry. Many chemicals now made in refineries and factories can be made by bio-based processes integrated into agroforestry systems. Biological substitutes include plant-based dyes, natural pesticides, neem, pyrethrum, chili pepper oils, essential oils for cleaning, medicine, fragrances, tannins for leather and preservation, resins, gums, and adhesives, fermentation-derived alcohols, enzymes, organic acids. Biological chemistry reduces toxic waste, fossil fuel dependence, and environmental contamination. Replacing pharmaceutical and biomedical inputs. Agroforestry systems can supply many medicinal plants and compounds that pharmaceutical manufacturing currently sources unsustainably. They can produce botanical medicines, turmeric, ginger, echinacea, ginseng, elderberry, aloe, antibiotic compounds from soil microbes and fungi, nutraceuticals, teas, extracts, salves, specialty mushrooms used in medicine. While modern pharmaceutical synthesis remains essential, natural compounds reduce pressure, diversify supply, and improve health access. Replacing textiles and clothing industries. Industrial textile production is highly polluting. Agroforestry and permaculture can supply renewable, biodegradable fibers. Systems can grow hemp, bamboo fiber, flax, linen, cotton in regenerative polycultures, wool, via silvopasture, edible oil trees for natural soaps and detergents. This cuts microplastic pollution, fossil fuel dependence, and water contamination. Replacing mining and metals. Partially, agroforestry cannot replace all mining, but it can replace large categories of materials used in consumer products. Possible biological substitutes: bamboo and wood for furniture instead of metal, mycelium composites instead of plastics and foams, plant-based carbon fibers, living fences instead of steel fencing, resin-based tools and structures. Reduced material demand combined with regenerative materials drastically shrinks mining's footprint. Replacing urban infrastructure and pollution control industry. Cities spend billions on storm water systems, cooling, filtration, and urban management. Permaculture and agroforestry offer natural alternatives. Nature-based solutions include green roofs to replace mechanical storm water systems, permeable landscapes replacing concrete channels, shade trees reducing cooling load and energy use, bioremediation replacing chemical water treatment, phytoremediation removing heavy metals from polluted soils, riparian buffers cleaning waterways. These systems reduce costs, improve air quality, and enhance livability. Replacing many transportation and logistics industries. A large portion of global transport exists only because supply chains are long and centralized. Permaculture and agroforestry localized production. Impacts: local food reduces global shipping demand. Local materials reduce freight emissions. Renewable fuel wood reduces petroleum dependence. Agroforestry-based settlements reduce commuting needs. Decentralized production shrinks the global logistics industry's carbon footprint. Replacing waste management and recycling industries. Regenerative systems transform waste into resources, reducing the need for centralized waste infrastructure. Permaculture converts waste into compost from organic waste, mulch from pruning, biochar from biomass, livestock feed from scraps, greywater irrigation, biogas from manure. This reduces landfill use, methane emissions, and pollution. Increasing social sustainability and equity by decentralizing production and giving communities control of their resources. Permaculture and agroforestry dramatically expand equity and justice. They generate local jobs, community-owned enterprises, income diversification, reduced dependency on extractive corporations, lower household expenses for food, fuel, and materials, more equitable access to essentials. Communities gain autonomy, stability, and resilience, replacing the need for many extractive economies. Instead of pulling resources out of nature faster than they regenerate, permaculture creates wealth by regenerating ecosystems. Benefits include growing soil instead of depleting it, rebuilding biodiversity instead of destroying it, restoring watersheds instead of draining them, strengthening community wealth instead of exporting it. This flips the economic system from extraction to regeneration. Why this works at a global scale. Permaculture and agroforestry use renewable processes, sunlight, photosynthesis, nutrient cycling, and biodiversity, to manufacture a wide array of goods and services. Unlike industrial systems, which treat nature as a dead resource base, regenerative systems treat nature as a living factory that becomes more productive the healthier it gets. This means productivity increases over time, environmental impacts decrease, economic equity grows, social resilience increases, climate stability improves, biodiversity recovers. Industrial systems destroy the future to produce the present. Regenerative systems improve the future while producing the present. A regenerative civilization. A civilization based on permaculture and agroforestry would be more like a network of living, self-renewing ecosystems than a collection of extractive industries. Local bioregions would manufacture food, materials, medicine, energy, and water services in ways that increase biodiversity and climate stability. This does not eliminate the need for all industries, especially those related to healthcare, advanced materials, and technology, but it replaces the most damaging 60 to 80% of today's extractive economy with systems that restore the planet instead of depleting it. How permaculture and agroforestry can replace industries and enhance global sustainability. Permaculture and agroforestry are ecological design systems that produce food, materials, energy, water, and ecosystem services by mimicking natural processes. Unlike conventional industrial systems, which rely on extracting non-renewable resources, polluting the environment, and centralizing production, regenerative systems use solar energy, living soil, and biodiversity to create continuous yields. By integrating plants, animals, and water systems, permaculture and agroforestry can replace many resource-intensive industries while increasing sustainability across ecological, social, and economic dimensions. Replacing industrial agriculture. Industrial agriculture depends on monocultures, synthetic fertilizers, pesticides, fossil fuels, and long supply chains. Permaculture and agroforestry can replace these systems by producing food through diverse, multi-layered, perennial systems. In these systems, fruit and nut trees, legumes, tubers, and perennial vegetables create continuous yields throughout the year. Nitrogen-fixing plants and composting cycles eliminate the need for synthetic fertilizers, while polycultures and beneficial insect habitats reduce or eliminate the need for chemical pesticides. These systems also store water in soils and reduce soil erosion, producing higher resilience and long-term yields with lower environmental impact. By replacing monocultures with polycultures, communities gain local, diversified, and sustainable food supplies while reducing greenhouse gas emissions from industrial farming. Reducing dependence on fossil fuels. Many aspects of modern industry, from transportation to plastic production to energy, depend on fossil fuels. Agroforestry and permaculture replace some fossil fuel uses by producing bioenergy and biomass locally. Trees, bamboo, and perennial grasses can be harvested sustainably for fuel or converted into biochar, biogas, or bio-oils. Plant-based materials can replace plastics, synthetic chemicals, and other petroleum-derived products. By decentralizing energy production and providing renewable, on-site energy sources, these systems reduce dependence on centralized fossil fuel infrastructure, lower carbon emissions, and increase energy security. Replacing timber in construction industries. Forestry for construction and industrial wood often destroys ecosystems and reduces biodiversity. Agroforestry produces renewable construction materials while restoring ecological health. Fast-growing trees, bamboo, coppice wood, and perennial fiber crops can provide timber, paneling, and structural materials. Silvopasture systems allow simultaneous production of timber and fodder while maintaining soil fertility. Mycelium and other plant-based composites can replace concrete, foam, or synthetic insulation. By integrating these materials into local construction, societies can reduce deforestation, minimize carbon emissions from building materials, and provide local economic opportunities. Replacing the chemical industry. Permaculture and agroforestry systems provide many natural chemical substitutes that can replace industrial chemical products, essential oils, plant-based pesticides, natural dyes, resins, and tannins can substitute for toxic chemical formulations. For example, neem oil, chili extracts, or pyrethrin derived from plants can replace synthetic pesticides. Compost and biochar serve as natural fertilizers, eliminating the need for synthetic nutrient inputs. These bio-based chemicals reduce toxic runoff, lower greenhouse gas emissions, and allow closed-loop cycles, in which nutrients are recycled rather than mined, synthesized, or released into the environment. Replacing industrial medicine and pharmaceutical inputs. While modern medicine remains necessary, agroforestry can provide a wide range of medicinal plants and compounds. Herbs, mushrooms, and perennial plants can supply antibiotics, anti-inflammatory agents, antioxidants, and nutritional supplements. Medicinal plants such as ginseng, echinacea, turmeric, and elderberry can be grown within food forests. This reduces reliance on industrial agriculture for medicinal crops and promotes local healthcare access. By integrating these resources, communities can supplement pharmaceutical supply chains and increase resilience to shortages. Replacing textile and clothing industries. Industrial textile production consumes massive amounts of water, energy, and synthetic fibers. Permaculture systems can provide renewable, biodegradable fibers including hemp, flax, bamboo, cotton grown regeneratively. Plant-based dyes, natural tanning, and woven fibers reduce chemical pollution. By producing textiles locally in regenerative systems, communities can reduce industrial pollution, carbon emissions, and microplastic waste, while creating employment opportunities in small-scale, decentralized production. Reducing the need for mining and heavy extractive industries. Although not all mining can be eliminated, many materials used in daily life can be replaced with biological and regenerative substitutes. For instance, bamboo, fast-growing timber, and mycelium composites can replace steel, plastic, and certain construction materials. Reduced dependence on metal and fossil fuel-based products lowers the environmental damage caused by mining, tailings, and chemical extraction, while promoting local, regenerative production cycles. Replacing industrial water management and pollution control. Urban and industrial systems rely heavily on mechanical water treatment, drainage, and pollution control. Permaculture landscapes perform these functions naturally. Swales, ponds, constructed wetlands, riparian buffers, and vegetated areas clean water, store rainwater, reduce flooding, and filter pollutants. Trees and groundcover reduce stormwater runoff and stabilize soils. By replacing centralized water infrastructure with living systems, communities save energy, reduce infrastructure costs, and improve water quality, while simultaneously increasing biodiversity. Reducing transport and logistics industries. Industrial transport exists largely because production is centralized and globalized. By producing food, timber, fiber, and energy locally in regenerative systems, reliance on long-distance shipping, fuel consumption, and logistics infrastructure is greatly reduced. Local production also decreases carbon emissions, creates local jobs, and strengthens community resilience. Decentralized production enables shorter supply chains and reduces the environmental costs of global trade. Replacing waste management systems. Industrial waste management is resource-intensive and polluting. Permaculture converts organic waste into compost, mulch, fodder, and biogas, closing nutrient cycles. Human and animal waste can be safely recycled in closed-loop systems. Agricultural residues become biochar or bedding, reducing landfill use. By designing systems that treat waste as a resource rather than as pollution, permaculture and agroforestry minimize environmental contamination while generating renewable soil fertility and energy. Social and economic benefits. Permaculture and agroforestry systems decentralize production, creating jobs, local income streams, and equitable economic participation. Smallholders, cooperatives, and communities can gain ownership of food, energy, and material production, reducing dependence on industrial corporations. By producing diverse products simultaneously, regenerative systems provide income stability and food security, which addresses inequity and poverty. Education, cooperative management, and community stewardship further strengthen local governance and resilience. How this increases global sustainability. Permaculture and agroforestry fundamentally change the relationship between humans and the environment. They increase sustainability by rebuilding soils and ecosystems, increasing long-term productivity, sequestering carbon, mitigating climate change, restoring water cycles, reducing drought and flooding, minimizing pollution, replacing toxic chemical industries, providing renewable energy and materials, reducing fossil fuel dependency, decentralizing economies, reducing transport emissions and inequality, increasing biodiversity, strengthening ecosystem resilience. Essentially, regenerative systems produce what society needs while healing the environment instead of degrading it, creating a positive feedback loop of ecological, economic, and social benefits. Permaculture and agroforestry offer a roadmap for replacing the most environmentally destructive and resource-intensive industries. By producing food, fiber, energy, medicine, building materials, and ecosystem services directly from living, regenerating landscapes, these systems reduce reliance on fossil fuels, chemicals, extractive industries, and centralized industrial systems. They simultaneously create resilient local economies, reduce pollution, restore biodiversity, and stabilize the climate. While advanced manufacturing, technology, and some specialized pharmaceuticals will remain, regenerative systems can replace the majority of extractive and polluting industries, establishing a sustainable, equitable, and resilient global economy.